All right, good evening, everyone. Thank you, everyone, for joining us tonight. This is the AIAA New England section's December webinar, and we're glad that you're able to spend an hour with us to be able to have this opportunity to listen to our guest speaker for tonight. So I will go ahead and introduce him. Before I do that, I want to just present myself. I'm Dr. Jason Hui, and I joined the New England Council a few months ago, and I'm working with the council to actually promote and extend our professional development program with additional speakers in the coming months. So I look forward to being able to share that with the entire section, and look for your upcoming communications on future webinars. So with that, I will go ahead and present our guest speaker for tonight. Professor A. Emrah Bayrak is an assistant professor in the School of Systems and Enterprises at Stevens Institute of Technology. He received his bachelor's degree in 2011 in mechatronics engineering from Sambonchi University, his master's of science degree in 2013, and his PhD degree in 2015 in mechanical engineering from the University of Michigan. Prior to joining Stevens, he worked as a postdoctoral research fellow in the Optimal Design Lab at the University of Michigan, and as a research scientist in the Integrated Design Innovation Group at Carnegie Mellon University. Dr. Bayrak's research focuses on integrating computational methods with human cognition for the design and control of smart products and systems. He is particularly interested in developing artificial intelligence systems that can effectively collaborate with humans, considering unique capabilities of humans and computational systems. He studies the impact of AI behaviors, division of labor, and coordination on trust and performance and human AI collaboration. His research uses methods from design, controls, and machine learning, as well as human subject experiments on virtual environments such as video games. So his talk tonight will be the new directions in human technology frontier, past, present, and future of human AI collaboration. Before we turn it over to Dr. Bayrak, I would request that if you do have questions, please leave it till the end after Dr. Bayrak has completed his presentation, and you can either then raise your hand, or you can enter your question in the chat, and we will then go through in order of the question being received. So with that, let's welcome Dr. Bayrak as he presents his talk tonight.
Thank you so much, Jason. It's a pleasure to present my work in front of such a great audience. Today, I will talk about some new directions in human technology frontier. So I will briefly talk about what happened in the past, where we are, and what are the emerging research questions in human AI collaboration. Jason already gave a brief background of where I'm coming from. I have, as you can see, a diverse background in mechatronics, mechanical engineering, and currently in systems engineering. So my research back in Michigan was mainly focused on designing vehicle architectures. And in Carnegie Mellon University, I started looking into how we could get humans and AI involved in design problems mainly, and I expanded that research to mainly decision-making in complex systems and environments. Today, I just want to give you a brief overview of what I have done and what are the emerging research questions in that area. Before jumping into the main theme of human AI collaboration, I want to give you a brief overview of how my research evolved into that direction, and you can see better why I'm studying that important problem. So back in Michigan, my main research focus was designing and exploring new vehicle architectures using traditional optimization techniques. So that could be applied to hybrid powertrain design, or that could be expanded into vehicle systems as a whole to find out new vehicle architectures. The main idea was to formulate this design problem mathematically as an optimization problem and try to solve that problem using different optimization techniques. Since these problems were mainly large and complicated, you cannot solve these problems in a single level. So what we used to do was to decompose that system into two levels. At the upper level, we were solving for what are the system level functional design needs. And at the lower level, we were looking into what we can do with the components that we have. And the main idea was to sort of coordinate these two optimization problems such that the functional design and the detailed design agrees on a common design problem. So we were mainly using existing optimization techniques to solve these problems, and the idea was to just fully automate this design problem. However, we have realized that the existing optimization techniques are very, very limited. So even something simple, obvious, became a very difficult job for some of the optimization techniques that we have. And we ended up spending so much resource on solving even relatively simple design problems. And if you want to design more than one vehicle together, that becomes easily intractable. So we have basically reached the limitations of the existing optimization techniques we have. And then we started to explore the idea to maybe get people involved in that design problem. Maybe we could combine the human intuition that could easily identify what is good and what is bad. And maybe we could augment that human intuition into some of the existing optimization techniques that we have. So, of course, to get humans involved, we did not formulate the complicated design problem that you see here. We wanted to see whether we could use just ordinary people. So for that, we decided to use games, where we formulated a relatively simple design problem, design and control problem, where people were supposed to design something in the vehicle powertrain and drive that vehicle over a track to see if their design is good, and iterate over their design to finally end up with a design that feel okay with. And their goal is to just get the highest score in the game, which means finding the best design and control strategy. So when we asked people to play this game, we got, I think, about 50, 60 participants. I don't remember the number exactly, but we got many people to play the game. And we collected the data that you can see on this slide. So in this data, each color represents a different individual. On the y-axis, you see how good their design and control strategy is. And on the x-axis, you can see how many times they play the game. So as you can see, there are a few individuals who played the game many times and performed relatively well. So this red line is the best that you can get in the game. So as you can see, this gray individual performed really good, but that individual reached there in about 150 gameplays. If you look at this red individual, that individual didn't play that many times, but found a relatively good solution very early. So which means that a lot of individuals could improve their score and get really nice scores early on. However, they just stop playing. On the other hand, if you use an optimization method never gets tired, right? So the methods just keep trying and trying over time. However, they cannot identify the little nice heuristics that people can do. What we ended up doing was augmenting the data that we collected from humans into an optimization technique. And the optimization technique, instead of blindly exploring the entire space, just explored the feasible space defined by this data set that we collected. And as you can see, the optimization technique also gradually improved its score over time. However, still worse than human data set that we have here. However, if you just let this algorithm play the game over and over a little bit more, I think in about like 1,000 trials, it reaches to what we get from good individuals, I would say, which gave us the idea that maybe this line of research is promising. Maybe we could combine human intuition with the existing computational techniques that we have. However, this is not really a human AI collaboration, right? So we were collecting data from humans and feeding that data into a computational method that we have. Our goal in the long run is to just, explore what we can do with human AI collaboration and maybe develop an architecture where humans and computers can work together. So the research that I did back in Michigan, I call it, is just a collaboration between computers, meaning we decompose the problem into multiple levels and solve these problems using multiple optimization techniques that we have, and we coordinated that. There was no human involved over there. With this game, we were basically feeding human data into a computer. In this talk, I will talk about architecture where we fed computer solutions to human decision makers to see whether it helps. And ideally, our ultimate goal is to just design an architecture where humans and computers can collaborate and learn from each other. In this talk, I want to give you a brief overview of where we are in this area, what we have done so far, and what are the emerging research questions. So the main motivation, as you can see here, is that humans and computers have unique capabilities. Humans are good at intuitive thinking, whereas computers are good at processing large amount of data. Computers cannot do intuition well, and we cannot do data processing as well as computers. But we have this complementary skill set which we could combine together to develop something better than humans and computers alone. And the application area for this line of research is various. I mean, you can think about smart defense, where soldiers can work with some intelligent systems like drones that fly over the area to do recon mission, or drones that operate on the ground to feed some intelligence to soldiers, or maybe do some of the tasks together. Or you can think about autonomous transportation, where vehicles drive themselves, maybe, and a human could control the fleet to tell vehicles where to go, which passenger to pick up, and so on. Or you can think of smart healthcare, where an artificial intelligence system could suggest doctors or nurses what to do based on the inputs from patients. So we could do you could develop systems that could outperform humans and outperform computers alone. However, we are not there yet. So there are a lot of issues that we need to resolve before reaching out to that end goal. Let me give you a brief history about that line of research to show you what we did in the past and how we came to where we are now. This research on humans and computers working together, it goes back to 1950s. So even though like human AI collaboration is a relatively new area, the collaboration between humans and machines dates back to about like 70 years ago. So in 1951, a researcher called Paul Fitts developed a list. Today we call that Fitts list, where he discussed what humans are good at and what machines are good at. And that line of research have been used to allocate functions between humans and machines in various domains like manufacturing. As you can see in that slide, that list was very primitive. According to Dr. Fitts, humans were good at detection, perception, judgment, induction, improvisation, and long-term memory, whereas machines at the time were good at speed and power, computation, replication, simultaneous operations, and short-term memory. And he was working in the area of aviation psychology, so you might be familiar with his work. Anyway, since then, a lot of researchers try to build their work on top of this list. This list was criticized multiple times, but it was a good guideline for us to think about how we could combine humans and machines. And until recently, we have been looking at how we could develop automation for human use. I intentionally use the word automation, but not artificial intelligence, because these systems were relatively primitive. They had a static nature, meaning that we defined the rules that these systems should operate on, and they were just, operating based on this rule-based logic. And the main goal of this line of research was to analyze what are the human factors that we should care about, like whether augmenting human thinking with some machine computation is good or bad. What are the important human factors that we should care about, such as workload, trust, and so on. And today, we have passed that type of automation, and now we are talking about truly intelligent systems, and look at whether we could combine humans with the current state-of-the-art artificial intelligence systems. They are different from the previous rule-based systems because they can adapt their decision-making. They can learn over time. As you feed these systems more data, their decision-making performance improves. They could learn from humans as they work with them. And now we can start thinking about these systems as a team member, as opposed to just using them as a tool. So some of these systems could operate as good as human beings. So if you find a good way to combine these AI systems with human cognition, we could get the real value out of these systems. What is AI? So I just briefly introduced you the difference between the current state-of-the-art AI systems and what we used to call AI in the past. So probably like in 1960s, AI was just an intelligent decision-making using computers. It was as simple as that. And computers were mainly operating based on rule-based logic, meaning that their sort of decision-making was sort of fixed, and they did not adapt their decision-making, but they could process large amount of data and make really fast decisions. But today we are talking about a different kind of computer-based decision-making. So right now we have some nice machine learning algorithms which could process data and develop some complicated neural network-based models, which relate a bunch of inputs to a bunch of outputs. And over there, they learn, what are the relationships between these inputs and how we could predict certain outputs that we are interested in by just, feeding these networks the real-time data. And artificial intelligence is basically a combination of these machine learning models to process these real-time inputs to make a decision in real time. So we don't necessarily understand how artificial intelligence make these decisions, because the model behind these artificial intelligence systems is so complicated. Even if you just look at a single machine learning model, the relationship between inputs and outputs is usually connected through a bunch of neural networks, which we can't really make sense of, because the inputs are they're related to each other in a very sophisticated way. And if you just want to understand how machine learning models make these decisions, it's very difficult for us to intuitively come up with certain explanations for it. And that makes artificial intelligence good and bad. It makes it good because maybe it's identifying certain relationships that we cannot understand. Those relationships may really exist. It's also bad in the sense that we don't really know what it is doing. And it's very difficult to verify whether that decision is a good decision or bad decision in a real world problem. And that creates a lot of issues. But those bottlenecks don't prevent us from doing really nice things with AI. Here's an example of what we can do with this sophisticated method to do something good. So this is a very recent news article where a group of computer scientists used an artificial intelligence method to finish Beethoven's 10th symphony by using his past work, meaning his previous symphonies, plus some of the leftover notes that he left to sort of get sense of what he was trying to accomplish. So an AI was trained based on past data, and that AI was fed with the notes from Beethoven in a systematic way, of course, to sort of predict what Beethoven was trying to do and finish his leftover work. And here is a link that you can just try and listen to it. And they have tested with some audience to ask them whether they can detect where Beethoven's actual work starts and where AI's actual work starts. And most of the people were not able to identify, which means that AI has done a pretty good job. However, the development of this AI was not as trivial as it sounds. So people did not just feed a bunch of data to AI to figure out, what is the remaining portion of Beethoven's 10th Symphony. They had to do a lot of development work to figure out, what are the different elements in a symphony, and train different models for different parts of the symphony. And they developed different models to connect these parts, and another model to assign instruments to the composition that the AI came up with, and so on. So these are the things that AI cannot come up with on its own, but rather there's a need for a human decision maker who knows the problem and guide the AI to come up with the right solution for each of these elements individually, meaning that a human cannot finish this job alone, an AI cannot finish this job alone, but rather we can create these nice things through human-AI collaboration. So when we talk about using AI to do the traditional work that humans do, people ask this question very often: is AI going to replace human workers? Is AI going to be a replacement? Is AI going to be just a tool like we use computers in the past, or is it going to be a peer? So my answer is probably AI is not going to replace humans, but AI is going to work alongside humans. And what it will do is to potentially transform the way we do our jobs, and it will enable us to do our job a little bit more efficiently. As I mentioned, AI has really nice capabilities, but those capabilities are not sufficient to replace what we can do really well as human beings: the intuitive thinking, making sense out of these decisions, and so on. So just to give you an example of what how AI could help us, maybe we can draw some similarities between human AI collaboration and some other collaborative work that we do in the real world. So I was reading a magazine just today to sort of figure out how other researchers look at this problem. And one researcher from University of Michigan gave that example. So the example is the collaboration between the police force and canine dogs. So these dogs have really nice capabilities that we don't have. So they can smell things very well. But they just don't know what they're doing. So they constantly need somebody to guide them to the right direction, and they can just help us find criminals, illegal substances, and so on and so forth, right? So this collaboration works really well. These canine dogs did not replace police officers, but rather they created a very nice collaborative work to do the job that maybe traditionally human officers used to do in a more efficient way. So I believe that human AI collaboration will evolve into that direction as well. So AI will change the way we do things, but it will make a positive impact. So what are the emergent issues that we need to resolve before making AI really useful? So if you look at the traditional AI research, people just develop AI for a purpose. And they design an AI to solve a predefined problem, and they never think about the human user. Their goal is to develop the best AI with maximum accuracy to perform the job in a most efficient way possible. these people adopt the notion of AI as a tool, or maybe as a replacement of humans. However, this is not, I believe, not the right way to make AI useful. So we need to start thinking about how we should develop AI to work alongside human beings. And that would probably change the way we develop AI systems. For example, imagine that there is an AI system to suggest certain things to a human user, like in case of, say, a doctor and computer relationship. So say a computer suggests doctor what to do. However, if the human user, doctor in this example, doesn't understand how AI works, then that relationship won't work very well, regardless of how nice or how accurate the AI is. If the human user does not understand the underlying principles or how the computer system solves a problem, then that relationship won't work well, and that AI will be useless. So what we need to do is to think about how we should develop AI considering the user in the first place. So I believe that there are like 3 domains of research that we need to address before making these systems useful. The first domain is about the mission design and coordination. So we need to think about the job as a whole, and understand, what humans are good at and what AI systems are good at, and think about how we should divide the overall labor between humans and AI systems. And we need to think about how we should coordinate the decisions between humans and AI. So there's something to do with the capabilities of humans and capabilities of AI systems. And the answer is probably going to change over time. Maybe AI is going to get better, or humans will maybe get used to the AI systems and their behavior will change and so on. So we need to think about that system level problem first. Then we need to think about human factors. Understand what are the unique things in human beings to consider when we are developing AI systems. Examples include like trust issues, the cognitive biases that humans have, and the workload issues, and so on. So if you overload humans, then even though we are capable at performing certain things well, under that stress, maybe we don't perform. Or if you just force a human to work alongside the AI, if there are certain biases from humans, then that relationship won't work very well, and the whole system is going to collapse overall. And there could be certain trust issues that we need to think about, and maybe build trust into AI so that we develop the right relationship in the first place. And finally, we need to develop the AI models that are adaptive to human thinking. So we need to think about the goals of the AI systems, and we need to build a transparency into the AI model so that when we look at it, we won't see this complicated, weird thing, but we will at least make sense of what AI is doing to help us understand what our teammate is doing. We should build this explainability into it. So I'm going to give you a brief sense of what are the sample research work that I'm doing in each of these domains. So I'm going to begin with this mission design and coordination. So we first look at the research questions like, what is the optimal task distribution between humans and some AI systems working together? And what is the best team composition? Say, you need to form a team of 3 or 4 people or machines. So how many people and how many machines should you have in a team to make the teamwork the most effective? So for these kind of problems, we look at basic decision-making under dynamic environments, where we think of machines as some autonomous agents that have certain capabilities, they have certain goals, and they have certain beliefs that they form about the environment based on their sensor data. And they use a reward structure that is created based on the observations and past experiences, and they react to the environment by performing certain tasks. And of course, while they're doing that, they have to work alongside with other machines or humans. So there has to be some communication and collaboration with other members. And human members in the team should also perform certain actions with the environment to basically work alongside with their peers to perform this overall task as a whole. And I'm not going to go into the mathematical details of this work, but we have used partial observable Markov decision processes to develop these autonomous agents. And we also model humans in a similar way, where these agents operate based on certain past experience and belief, and their current observations about the environment, and the information coming from their peers to make decisions about the environment. The application problem that we picked is a disaster relief scenario. This is a problem where humans and autonomous agents have different capabilities, and the environment demands certain things like extinguishing fires and rescuing people in certain locations. And this demand is dynamic, meaning that if you just don't extinguish fire, it just gets bigger and bigger. And certain people are scattered around a certain area, and you don't know where they are, so you need to sense and find them, and so on. And there is a limited communication between these agents, meaning that whatever an agent senses from the surrounding, it doesn't directly transmits to other agents. So we tried to formulate a realistic scenario to look at, what is the ideal team composition. And while we are making that investigation, we need to make certain assumptions. And we intentionally made human agents inferior to their autonomous counterparts to see whether, including humans in these teams is beneficial or not. So let's say there is a bunch of robots that are superior to humans. However, they make decisions based on what they consider optimal. And human agents, even though they're inferior in terms of capability, they don't always act based on what is considered optimal, but they also explore the area a little bit. So they go beyond what is considered optimal. And once we analyze that in a team of 3, here are the results that we get. So the numbers don't matter much, but what I want to show you is that when there are no humans in the team, the mean performance is 220 with respect to some unit, which is not relevant. And if you have 1 human in the team, the performance increases to 250. And if you have 2 humans, it drops back to 130. With 3 humans, it drops down to 127 or so. So which means having no human, meaning creating a team entirely of autonomous agents, is not that good. It's because the environment is dynamic. So as I mentioned, these agents don't go beyond what they consider optimal, and they don't do exploration much. And we designed human agents intentionally to be some noisy decision makers to reflect what we could normally do in the real world. So we don't always act on what is considered to be optimal, but we also look around and sometimes deviate from that and explore a little bit. And we found out that humans who have lower capabilities than autonomous agents could be beneficial to the team, which means that finding out the ideal team composition is not a trivial task. We cannot just make that decision based on the capabilities, but we also need to think about the decision-making process that humans have. And maybe in real world, if we just model humans in a more realistic way, maybe we could find out different answers. But my point is that the answer to this question is not that trivial, and there's a lot more work to be done. So the other area that I work on is human factors, where we need to investigate issues related to trust, cognitive biases, and workload. My particular focus is trust in artificial intelligence systems. This problem is very, very important because the amount of trust that humans have directly affects the value that we get out of this human AI collaboration. And there are a few extreme examples where you can see that trust issue really is detrimental in the effectiveness of human AI collaboration. One example that I picked is from an accident where a driver trusted in autopilot in a Tesla vehicle a lot more than he or she was supposed to do. So considering that these systems are not perfect, we should not just trust these systems blindly, but we should have a healthy balance of trust and some skepticism. Without that, so we can end up with some fatal situations like that. And there's an example of where having a lot of trust in these systems is not good. On the other extreme, if you look at some other artificial intelligence system, you can find examples where trust, not having trust really hurts the value of these systems. Here, I show you IBM Watson, which is an AI designed to guide clinical decisions. And there are a lot of trust issues from expert users like doctors. Doctors mainly just don't trust the current state-of-the-art AI systems developed by IBM. And there are a few reasons for that. First, say doctor has a belief about a patient. Say, doctor believes that a patient is sick. If AI tells the doctor otherwise, doctor usually tend to believe their own decision-making more than what is suggested by a machine whose underlying working principles is unknown to the doctor. And if the suggestion is in line with doctor beliefs, then there's no need for that system in the first place. So the trust issues just hinders the benefit that we could get out of these systems. So what we need to do is to address these trust issues, meaning that we need to build trust into the design of the system. And we need to develop the healthy balance between trust and skepticism. So in our research, we identified several factors that affect this trust relationship. So these factors include some features related to the design of the system, certain characteristics related to the task, and certain attributes related to humans, such as culture, knowledge, awareness of the user, attitude, etc. We need to consider all these factors together when we are developing the AI. It's not just developing the right machine learning model, but building a system considering all these factors together. We also look at what is that healthy balance, like how much we should trust in an imperfect artificial intelligence system. So for that, we modeled humans as imperfect decision makers, and AI is imperfect decision maker too. And we modeled humans to have certain self-confidence and certain bias toward the system and so on. And we performed a study to figure out what is the ideal level for self-confidence and bias given an imperfect human and given an imperfect system. And we figured out that the answer is not trusting the system entirely or the other extreme, but somewhere in between. And that answer varies based on problem and varies based on the capability. But we could quantify how much a user should trust a given system. And if we know that, we could build a system considering that. If we realize that human has too much trust in a system, maybe we could give some warning to humans saying that, hey, you're just relying on me too much. Just use your own decision making a little bit more. Or if we realize that human doesn't trust the system at all, then maybe we should mitigate that through several interface changes and so on. Finally, we need to develop the AI system such that it adapts to human decision making. This is where I'm going to show you the architecture that I showed you at the very beginning. Again, we were looking at a dynamic decision-making problem over time. But in that case, we were looking at a problem where there is an opponent. So in real world, it could be a problem that represents what we could see in military environment, or it could represent a problem where we see competition in the real world. Say there is a company like Uber that is competing against a company like Lyft, and we need to make a decision to basically control the agents that we have. So for that problem, since we could not model what's happening in the real world and collect data from it, we decided to use, again, video games, where there's already a problem implemented. and there is plenty of data available. So we decided to build an AI model that solves this problem and makes a recommendation to a human user and adapts its decision making based on what human does. So for that, we integrated controls, game theory, and machine learning. I'm going to skip a bunch of details in the middle to describe how we developed that system. But there is a sophisticated set of models that we have developed to end up with the model that I'm going to show you. So I'm going to skip these slides. These are sort of technical details of how we did it. But here is the result that we obtained. So the AI solves the problem in a game called StarCraft and suggests certain things at the beginning without taking any input from the human. So these are just predefined set of suggestions to open the problem, I would say, and then transition to an adaptive decision-making process based on game theory to make recommendations to humans. And here we compare the actual human decision-making data with what could happen if people followed the suggestion from the computer. And we found out that there are like good players and bad players, meaning those players who won the game and those players who lost the game. And we realized that those who won the game do not need any suggestion from the AI, so they could be better off by just following their own decision-making process. And those who lost the game could benefit from the suggestions from the AI. So which means that human AI collaboration does not always improve decision-making. There are certain cases where we could use AI to improve decision-making, and there are certain cases where we could be just better off if we just rely on our own decision-making. So following that, we wanted to put that into practice and see, if we just use an AI like that in the real world and get actual humans in the loop, what would happen? So we designed an experiment where AI suggests certain predefined strategies to a human user, and then switches to a game theoretic phase where AI adapts its own decision making based on what actual humans do, whether they follow the suggestions or not. And here are a few current findings. We haven't published these results yet, but we are sort of going to publish very soon. Our current findings are in line with what we have found computationally. So once we perform an experiment with expert users, we have found out that AI does not really improve their performance. They were trying to follow the suggestions from the AI because it was an experimental environment. I guess they felt like they should follow. And when they do that, their performance just decreased compared to what they would do on their own. And we did not really get a lot of benefit from the AI. And that's because AI suggests some sort of a safer approach than what they would do if they played the game on their own. And then now we are performing an experiment with novice players. And our expectation is that AI could help these novice players a lot more than it helped the expert players, because maybe novice players, they don't know what they're doing, and maybe they need some guidance from an AI that could sort of tell them what to do until they feel comfortable with the environment. So we are currently collecting data from that, but this is our expectation, which means that this developing AI to help humans is not a trivial task. We need to consider all these factors together to develop the right system for the right purpose. So that's what I am hoping to do in my own research. So right now, we know the capabilities of AI. We know a lot of things about human factors, but we haven't basically integrated them together to develop a set of principles for us to follow in developing an AI system to effectively collaborate with humans. And there are so many open research questions in that area, as I mentioned. So that's pretty much all. I just don't want to take a lot of your time and leave some time for questions from the audience. With that, I'll leave it to Jason again.
Okay, thank you, Dr. Bayrak. We can open it up to questions. So if there's anyone who has a question for Dr. Bayrak, feel free to either, I believe you can unmute yourself, or you can enter in the chat window. So let's see. I have a question. So Dr. Byrak, so you mentioned about artificial intelligence, and obviously, um, you know, um, that the collaboration with humans is not trivial. Can you think of some applications? So you had talked about complex systems in the previous slide. Um, um, Obviously you have some things that you're looking into. Do you know if there's also some complex systems such as aviation or aerospace that involves artificial intelligence that is currently in the research phase, or it's what is the long-term strategy for incorporating artificial intelligence within those types of systems?
So that's a very good question. As far as I know, defense systems are looking into that area heavily. So whether they are, systems that operate on the ground or up in the air, the Department of Defense is heavily investing in that domain to see what we could do to combine human intuitive thinking with the capabilities of AI. So the results that I presented was funded by DARPA, actually. And over there was a program called A-Teams, Agile Teams, where they were trying to build teams of humans and some intelligence systems. And they were trying to assess whether combining the human thinking with these systems improve the decision-making performance of humans alone. So I believe that Air Force is heavily investing in that area as well. There are so many programs under Air Force where they're investigating the finding the calibrated level of trust. So when I was talking about a trust problem, I mentioned that the trust should not be maximum or minimum, but somewhere in the middle. So there were some Air Force programs where they were trying to quantify this calibrated trust in a complex aviation environment. So, so defense is one. So I know that the transportation is another area where the work with autonomous vehicles basically go alongside with what we can do with automation and what we can do with humans. So how we could sort of combine the capabilities of both decision makers. Right now, if you look at the autonomous cars, it's basically a collaboration between human and AI. So we don't just let AI drive the car, but human always has to be in control. Also in healthcare environment, we see a lot of research on how we could develop AI systems where we could combine the human decision making, like doctors and nurses and so on. But there are a few issues that sort of make the implementation a little hard. First of all, there are no good regulations about AI. Let's say there is an AI developed to sort of help humans. How are we going to know that it's safe for humans to operate? So for that, we need to have like really nice test beds where we verify and validate the performance of AI. However, the kind of AI that I mentioned is just dynamic, right? So it learns over time, then its capabilities change over time. So if you have such a dynamic system, say you can verify now under certain operating conditions, but if it changes tomorrow, then it won't be a verified system. So therefore, implementing these systems in practice has a lot of bottlenecks from regulation side and from safety side and so on. So I believe that we're going to get there not just next year. So there are a lot of things that we need to figure out on the way. So that's why we don't see these systems in practice a lot.
Okay. Yeah, I was also thinking, obviously, air traffic controls, obviously that is going through, almost a next generation design, and that's very complex. And would artificial intelligence, be beneficial in that type of scenario where it may improve the human collaboration?
Yes, so thanks for mentioning that. I also seen a lot of work in that problem as well. So air traffic control is one of the benchmark problems in the aviation area. So when I was presenting what was done in the past, so a lot of human AI collaboration work was done specifically on that problem. And we figured out a lot of issues like trust and workload and cognitive biases and so on in that benchmark problem. Right now, in the past, though that kind of research was limited to just formulating this air traffic control as an optimization problem and see whether we could just present the results of optimization problem to humans and see whether that helps human decision makers. But right now we can benefit from the capabilities of AI, which can process a lot of data, historical data, to build sophisticated models that we cannot just build on our own, and provide some suggestions to human decision makers. And over there, I think there is a lot of room to benefit from that collaboration as well.
Okay, great. So any other questions from our attendees?
I have one question, Dr. Berg.
Yeah.
So in the management science, there's diversity and broadening a background in a collaborative group is a big topic. In your research, I think sounds like collaboration is focused on AI and a person, I guess.
Mm-hmm.
Any insights on how could, say, when we have to drive a complex decision, perhaps AI can contribute in a setting that multiple team of humans could operate with AI?
Mm-hmm. So over there, we still don't know what is the ideal architecture to get AI involved. So the scenario that you're describing is that there are multiple humans that make decisions right now, right, without any help of AI. The question is, how can we just integrate AI into that teamwork? So there are so many possible architectures that people are currently exploring. One possible architecture is where every human decision maker has its own decision support system, where the ultimate decision maker is still humans, but it is supported by every person's individual AI helper, I would say. An alternative approach is to think about this problem as a whole and see what are the kind of problems that the artificial intelligence can solve on its own. So that is usually dependent on what kind of data is available, what kind of models that we can build using that data, and how effective the AI systems can solve these problems. So it's an open field. So I recently wrote a proposal to NSF to explore that problem, where I look at this complex problem in an enterprise where there are so many levels of decision making involved, from management to lower level, like operating systems kind of decisions. And over there, if you want to sort of integrate AI into that enterprise, how can you transform that enterprise into a new model where humans and AI systems perform the same task in a completely different way, in a completely different organizational architecture? It's an open field, but my guess is that the kind of organization structure that we can come up with human AI teams is going to be completely different from what we currently have with human teams alone. So I can tell that it will be totally different, but I cannot tell you what it is going to be exactly. That is still an unknown, uncharted territory, I would say. The most of the AI research currently is focusing on, how can we make AI better to solve a given task? Unfortunately, this is a very limited vision of AI, and I believe that we have to go beyond that to make the AI systems useful. And there's so many opportunity to completely transform the way things we do currently.
Okay, thank you.
You're welcome.
Okay, any more questions? Okay, So thank you, Professor Bayrak.
Thank you so much.
For spending the time with us this evening to give your talk. Just a reminder, we do our next webinar will be in mid-January. There will be a notice that will go out, as well as it will be posted on the New England section's website. And it will be actually talked by Paul Bevilacqua, who is, he will be speaking on inventing the F-35 Joint Strike Fighter. So that will be an interesting talk. He will be giving a history of that actual 5th generation aircraft. So look forward to folks being able to attend that webinar. So with that, thank you everyone for joining us, and we will see you next month.
Thank you so much for inviting.
Thank you.
It was a pleasure. Bye-bye.
Bye-bye.